Hello, Abstract Math. Once again, we meet to discuss wonderful things. And we're going to talk about roots. We're going to talk about the completeness axiom. So let's pray and let's start talking about talking about roots. Father, thank you for the knowledge that you've given people about mathematics, the knowledge that you've given us about science, about technology, about medicine. Lord, how you've taken care of us. And Father, I pray for all of those who are affected by COVID-19 that you will take charge, that you will heal many. Lord, we know that you're still in charge, you're still on the throne, and so I pray, Father, that you will do what is easy for you, that you will heal, and that you will cause yourself to be glorified in all that's done. And I thank you for this class. I thank you, Father, for giving us understanding, and I trust you to do that today during this lecture. In Jesus' name, amen. Okay, we're going to begin by defining nth roots of numbers. And of course, you learned many years ago that if you want to stay within the real number system, you can't define some roots. So let's see when you can and when you can't. Definition. If b is a real number and n is a natural number, so 1, 2, 3, 4, 5, etc., and if kind of case 1, b is greater than or equal to 0, then a is called an nth root of b, and we write a equals the nth root of b if a is greater than or equal to 0. I'm going to do case 2 in a moment, but let me talk a little bit about that requirement that a is greater than or equal to 0. If you think about the square root of 4, the square root of 4 we've always been told is 2. It is 2. The square root is unique if there is a square root in the real numbers. And we're going to actually prove that in a few moments. But the fact that I require that a be greater than or equal to 0 precludes the possibility that people would think that negative 2 is also a square root of 4 simply because its square is 4. So if I start off with a positive number, its square root has to be a positive number. And of course, a to the n equals b. So if b is greater than or equal to 0, then a is called an nth root of b, and we write a equals the nth root of b if a is greater than or equal to 0 and a to the n equals b. Those are the two requirements. Okay? Now our if still holds here. If b is less than 0 and n is odd, a is called an nth root of b, and what requirements do I have here? Just that a to the n equals b. And we write it the same way, that a is the nth root of b. Okay, so for any positive number, I can take any nth root of that and it will be a positive number. For any negative number, I can only find the nth root of that negative number if n is odd. I can find a cube root, a fifth root, a seventh root, but I can't find a square root or a sixth root or a 12th root. So those are the provisions. Now, for those of you who know something about complex numbers, with which we're not really going to be very interested this semester, but you know that it's possible to take even roots of negative numbers as long as you allow complex answers. But we're not allowing complex answers. We're requiring that b be a real number. Okay? Note that if the nth root of b exists, it is unique. This is a comment that I referred to a little while ago. I told you that we were going to prove it. So let's prove it. The faith step, right? Suppose there are two of them. This is always how you prove uniqueness. You prove that something is unique by saying if there were two of them, then the two were actually one. So if c is equal to the nth root of b and d is equal to the nth root of b, suppose that those two things are true. Okay? Then c to the n equals b, that's the definition, c to the n equals b, and d to the n equals b. So that means that 0 is equal to c to the n minus d to the n, for sure, right? But this can be factored. I can pull out a c minus d, and with what am I left? See how I didn't end that with a preposition? If I pull out a c minus d, then in order to get this c to the n, I'm going to need a c to the n minus 1 in the other factor. But now I'm stuck with minus d to the, I'm stuck with a minus c to the n minus 1 times d, so I'm going to need a plus c to the n minus 1 times d. See how I did that? So I've got c to the n, which I wanted, but I'm stuck with negative c to the n minus 1 times d, so I need a positive c to the n minus 1 times d to cancel it out, because that's not in here. And so I have it in the cross term, c to the n minus 1 times d with a plus sign. But now I'm stuck with minus c to the n minus 2 times d squared, so I'm going to need a plus c to the n minus 2 times d squared. And that continues all the way until I get to the a d to the n minus 1. But now I'm stuck with minus, this is minus 1. I said it, but I didn't write it. I'm stuck with a d to the n minus 1 times negative d, but that's exactly what I want to be stuck with. So that is my other factor, which I'm going to call a. C minus D times A. So A is this. All right? Now, if C doesn't equal D, I'm claiming that it does. If C does not equal D, for contradiction, it's not a very good does not equal. Well, that means that C minus D is not zero. Well, if C minus D is not zero, but these two things multiplied together are zero, then A must be zero. So A must equal zero. Okay? Now, am I going to break this into cases? Yes, I am. Case 1. If B is greater than 0, then by our definition, I have to have that the root is greater than 0, and both of those are roots, so C is greater than 0, and D is greater than 0. So C to the n minus 1 plus C to the n minus 2 times D plus all of these are positive numbers, so A is greater than 0. Contradicting that A must equal 0. Okay. Case 2. If B is less than 0, and of course if B is less than 0, I'm requiring that n is odd. So with n odd, then just apply case 1 to negative C and negative D. Which are both positive. Okay, and that's the end of that. Thus, in each case, we've contradicted that C does not equal D, so C does equal D, and that's the end of the proof. And I'm going to get another pen because this one's starting to fade out a little bit. Okay, progress. Another way of writing the nth root of B, by the way, notation. Holy cow, that's much better. Notation. The nth root of B is also written as B to the 1 over n power. And let's make a definition. B to the m over n power is the same as the nth root of B to the m, which is the same as the nth root of B to the m, which is the same as b to the m to the 1 over n, which is the same as b to the 1 over n to the m. All of those are the same way of writing b to the m over n power. Now, I would recommend that you practice what I'm about to practice with you, namely getting familiar with these fractional exponents. So let's practice. I wish that we were together so that I could hear your wonderful voices yelling out the answers to the things that I'm going to be saying. But I trust you. I trust that you will actually yell out the answer to the things that I'm about to quiz you on, just for practice. For example, let's start easy. What is 8 to the 1/3 power? How many people said 2? 8 to the 1/3 power is the cube root of 8, which is 2. How about 4 to the 1/2 power? Everybody said 2, hopefully. What is 32 to the 1/5 power? That's also 2. Let's see if I can get away from 2 here. What is 64 to the 1/2 power? And the people all said 8, right? What is 125 to the 1/3 power? And the answer is 5. Now, what is 125 to the 2/3 power? 125 to the 2/3 power. Well, that's the same as 125 to the 1/3 power squared. So if 125 to the 1/3 power is 5, 5 squared is 25, then 125 to the 2/3 power is 25. Hopefully you're keeping up. Maybe some of you are ahead of me. Keep yelling out those answers. What is 27 to the 2/3 power? I think I heard a 9. I hope so. Now, we're going to be studying negative exponents. In fact, we know what negative exponents are. We had that theorem, I think it was 5.18, but it talked about what happens with negative exponents, so let's practice some of those. What is 8 to the negative 2/3 power? Remember that a negative exponent just means that the number's in the wrong place. If it's in the numerator and you have a negative exponent, then put it in the denominator and it'll be a positive exponent. So 8 to the negative 2/3 power is 1 over 8 to the 2/3 power. Well, that's the cube root of 8 squared in the denominator. Cube root of 8 is 2, 2 squared is 4, so the answer is 1/4. Anybody yell that one out? I hope so. What is 27 to the negative 2/3 power? And the answer is 1 over 9. What is 81 to the 3/4 power? Well, the fourth power of 81, the fourth root of 81 is 3. So 81 to the Did I say 81 to the 3/4 power? That's what I meant to say. So if I didn't say that, pretend that I said that. 81 to the 3/4 power is the fourth root of 81 cubed, which is 27. What is 81 to the negative 3/4 power? And the answer is 1 over 27. Okay, last one. What is 128 to the negative 4/7 power? 128 to the negative 4/7 power. Negative means it's in the denominator. Seventh root of 128 is, let's see, what is that? Oh, it's 2. 2 to the 4th is 16. The answer is 1 over 16. So wouldn't hurt you to practice some of those if you didn't get most of them. That's going to come in handy. Remember at the very, very early stages of our class, I showed you a proof by contradiction that the square root of 2 was an irrational number. I'm going to show you that proof again. Make sure that you write it down. Hopefully, when you take notes in any class in mathematics, you don't just sit and listen. If you take notes in a class, when I was taking notes in mathematics classes, I wrote down as fast as I could every word that the instructor said. Even the prepositions, the adjectives, I wanted to make sure I caught everything. So take incredible notes all the time in all math classes. Probably the most important thing that I can tell you this entire semester. Take really good notes, as much as is possible, word for word notes in every math class, so that when it comes time to study for exams, you've got the whole lecture in front of you, and all you have to do is just remind yourself of everything at that time. I want to redo the proof that the square root of 2 is an irrational number. And it's going to take a little more space than I've got there. So let's erase a board. So consider this a CVS instant replay, only not so instant since it's been several months since you saw it last. But recall the proof that the square root of 2 is irrational, meaning it's not a fraction. The proof went like this. By contradiction, suppose it is rational. Suppose the square root of 2 is rational. And so write it as a fraction. Right? The square root of 2 equals a over b, which is a fraction. This is a comma, a terrible one. It's a fraction in lowest terms. Okay. Now, square both sides to get rid of this square. So therefore, 2 equals a squared over b squared. Hence, clearing the fraction, this is a comma also. Hence, 2b squared equals a squared. Okay? Now, that means a squared is even. Thus, a squared is even. So a is even. Since if a were odd, then I could write a is equal to some even number plus 1, and that implies that a squared equals, copy, 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 2k plus 1 quantity squared, which is 4k squared plus 4k plus 1, which is odd. Not even, and a squared is even. So if a squared is even, then a is even. All right? Since a is even, we can write it as 2 times k instead of 2 times k plus 1. I don't know what k is. But if a is even, which we've now determined that it is, I can write it as 2k. Now I'm going to take this value for a and I'm going to plug it into this equation. So, copy, 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 2b squared is equal to a squared. Which implies that 2b squared, now let's square this, that's 4k squared. Therefore, if I cancel a 2 on both sides, b squared equals 2k squared, so b squared is even, so b is even. Now what's wrong with that? A is even and B is even. So B is equal to 2 times something, let's say call it 2 times M. But then A over B is 2K over 2M. Got to stop erasing with my finger. That means A over B was not in lowest terms. And that is the contradiction we were after. Contradiction. So what does it contradict? The very beginning, that the square root of 2 is rational. So the square root of 2 is not rational. And that's the end of the proof. Okay. Let's erase another board. I wanted to show you that proof one more time, just because that could come in handy in the future. Let's shift gears a little bit now and talk about some properties of functions. Definition. if f is a f and g, I'm gonna have two functions in here. If f and g are functions mapping a set X into the real numbers, then f plus g is defined by f plus g of x is equal to f of x plus g of x. Okay? This is not a distributive law. We're not talking about multiplication here. This is this function evaluated at that point. Okay? The function f plus g evaluated at the point x means I take f evaluated at x and I add g evaluated at x. Similarly, f minus g is defined in the obvious way. I subtract the two function values. Fg is defined in the obvious way. I multiply the function values. And f divided by g, I have to be a little careful with. This maps x slash 0 into R by f over g evaluated at x is the quotient. Sorry, that's not the way I wanted to write that. Forgive me for that one. I'm going to define another set. It's going to map x sub 0 to R by this equation, where x sub 0 is the set of all x in x such that that denominator is not 0. So sorry about that. So x sub 0 is a set of all the things at x that do not land on 0 when I plug them into G. That's the set that gets mapped into R. Okay. Now another definition, several definitions in fact. You're familiar with these if you've taken calculus. I think everybody here probably has. But just reminder, and we've been using some of this terminology before, but I want to make it official now because we're going to be doing some problems with them. Okay. Definition. Let I be any interval in R. Now remember, there are four kinds of intervals. There's an open interval, which excludes both of the endpoints. There's a closed interval, which includes both of the endpoints. And then there's left open right closed, which includes the right endpoint and excludes the left endpoint, and then you can do it the other way around. So there are 4 different types of intervals, and I don't care which one we're talking about. I is any interval in the real numbers. Okay? And F is going to map I into R. And that function is said to be increasing on I if A less than B, gotta stop erasing with your fingers here. If A less than B implies f of A is less than or equal to f of B. Now, you may have seen this definition with a less than sign, in which case you talked about a function being increasing and then non-decreasing, which for some people is a confusing terminology. So we're going to fix that by saying the function is said to be increasing if this is true, which really means it doesn't decrease, okay? If f of A is less than or equal to f of B, so if A is to the left of B, then f of A is below f of B, or equal to. All right? It's called strictly increasing. If A less than B implies that f of A is strictly less than f of B. It's called decreasing if A less than B implies that f of, which way do I want to put it? It doesn't matter, but if f of A is greater than or equal to f of B, and it's called strictly decreasing, and I'll bet you can figure this one out for yourself. If A less than B implies f of A is strictly greater than f of B, and these are assuming that A and B are in the interval in question. Okay? All of those. So let's do some examples. Where is f of x equal to x over 1 minus x, increasing, decreasing, strictly increasing, and strictly decreasing. Well, let's do the arithmetic. Hopefully everybody already knows how we start, right? You always start these things with finding the domain. Finding the domain of a function is the 0th step of doing anything with that function, okay? So the 0th step is finding the domain. The domain of f is what? What's everything except 1? So it's all real numbers except 1, which you could also write this way. Okay. What's the second step of dealing with a function? And you all know what it is. It's taking the derivative. Because to take the derivative, that gives you the critical points. Getting the critical points shows you the max, the min, when it's increasing, decreasing, all that kind of stuff. So let's do that next. Actually, next is going to be to erase this board. Don't need notes for this. Okay, so let's take the derivative of the beast, and hopefully everybody remembers the quotient rule. If you don't, go back and study it, because math builds on itself. You'll definitely need quotient rule and product rule for this class and for all classes that you take afterwards. But f prime of x is the derivative of the top times the bottom minus the top times the derivative of the bottom, which is -1, all divided by the bottom squared, right? And that's equal to 1 minus x plus x divided by 1 minus x squared, minus x plus x, and the people all said poof. Hopefully you said poof. And that gives me 1 over 1 minus x squared. All right? Now, how do you know when a function is increasing, strictly increasing, etc.? If the function is differentiable, which this function is every place except x equals 1, then the function is increasing when the derivative is greater than or equal to 0. It's strictly increasing when the derivative is greater than 0. Now, what is the sign, the SIGN, of that derivative? It's positive on top, it's positive on the bottom. The sign is it's greater than 0. So this function is always strictly increasing on this domain. But we defined strictly increasing for intervals. And the domain is made up of 2 intervals. So it's strictly increasing on each of them, on -infinity to 1 and on 1 to infinity. Okay? It's never decreasing, never strictly, okay? It's always strictly increasing. Let's do another example. I have fun doing calculus. I hope you do too. F of x equals x squared minus 1 over x squared plus 1. So, what is the domain of this function? Where does this function get into trouble? And the answer is, it never gets into trouble, because the denominator is always positive, it's never 0, so the domain of this thing is everything. The domain is -infinity to infinity, all real numbers. So the first step after that, because that was the 0th step, f prime of x equals the derivative of the top, 2x, times the bottom, copy, 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 minus the top, copy, copy, times the derivative of the bottom, which is 2x, all divided by the bottom squared, which is equal to 2x cubed plus 2x minus 2x cubed plus 2x all divided by the bottom squared, or the new bottom, x squared plus 1 squared, which is equal to, and the 2x cubes go poof, and I've got 2x plus 2x, which is 4x up on top, divided by the bottom squared. Now, the bottom squared is always positive. The top, however, can be 0, negative, positive. So what you do is you find the critical points. It's obvious that the only critical point here takes place at x equals 0. So this equals 0 at x equals 0. And then we use the first derivative test. What happens to the left of 0 and to the right of 0? To the left of 0, the top is negative, the bottom is positive, so f prime is negative. So to the right of 0, x is positive, 4x is positive, positive over positive is positive, so f prime is greater than 0. Now what's happening when the derivative is negative? The function is decreasing. Strictly decreasing. And then at 0, it turns around, starts increasing. They say it's very important to do sound effects when you do calculus, right? So we don't care at this moment, but there is a minimum at x equals 0. But the answer to the question is it's strictly decreasing on negative infinity to 0, including 0 this time. And it's strictly increasing on the interval from 0 to infinity, again, including 0. Now, you may be wondering about something. 0 got included in the interval where it was strictly decreasing and in the interval where it was strictly increasing. The reason that that's not a problem is because there's no such thing as increasing at a point. There's only increasing in an interval. And so having 0 be in both of those intervals is no problem because I need to be able to compare two values in order to say increasing or decreasing. And it doesn't hurt that 0 is one of those values if a number is positive or one of those values if the number is negative. So this is how you do all of these. Just take the derivative, first find the domain, then take the derivative, and then the sign of the derivative tells you about increasing, decreasing, etc. Okay? Let's see. Let's prove a nice little theorem here. We've seen already this semester that it's important to know when a function is one-to-one, because sometimes you care about solving equations which require finding an inverse function. And of course, the inverse of a function doesn't exist unless the function is one-to-one. So there's a nice test for when a function is one-to-one. If you have a graph, you already know that a function is one-to-one if it passes the horizontal line test. Vertical line test is a test to see if it's a function. Horizontal line test is a test to see if it's one-to-one. But a really nice test for one-to-oneness is if it's strictly increasing or strictly decreasing. So if f is strictly increasing, and I'm going to put in parentheses, or strictly decreasing, either one, then f is 1 to 1. Proof. And this is pretty easy. Now, how do you prove that a function is 1 to 1? What does that mean? It means if two function values are equal, then the inputs had to be equal. That's really what the horizontal line test means. Here's a function that is clearly not 1 to 1 because f of a and f of b are equal, and yet a and b are not. So 1 to 1 means if f of a equals f of b, then a equals b. And this function doesn't satisfy that condition. But if the function were strictly increasing or strictly decreasing, then it does satisfy that horizontal line test. It is 1 to 1. However, this definition does not depend on being able to draw a graph. It doesn't even depend on the function having anything to do with real numbers. It's a purely algebraic theorem. But the proof is going to depend on the real numbers. If f of a equals f of b, where a is less than b, this contradicts strictly increasing, which says f of a is less than f of b, and it contradicts strictly decreasing, which says the opposite. F of a is greater than f of b. Both of those are a contradiction to f of a equaling f of b. That's the end of the proof. That was easy, right? Now, we're going to go on to another topic. The topic is roots of polynomials. And before we go on, let me talk a little bit about the word roots, because I want to make sure that there's no confusion here. A few moments ago, we talked about roots, as in square roots, cube roots, the ninth roots, all of those, the nth root of b. That's not what we're talking about here. When you talk about roots of a polynomial, you're talking about the places where the polynomial is 0. The roots of a polynomial are the places where that polynomial is 0. Now I'm going to take a drink of my, well, I think it's iced tea, right? Yep, it's iced tea. Sometimes the throat just feels like the Sahara Desert. Okay. So let's take a few polynomials as examples. X squared minus 6x plus 9. X squared minus 6x plus 9. What are the roots? And by the way, many times people use the word zeros, meaning places where the polynomial is 0. What are the roots of x squared minus 6x plus 9. And it's easy to answer, just factor the beast. I know I need an x at the beginning of both. Two numbers that multiply together to give me 9 and add together and give me negative 6 have to be negative 3 and negative 3. So the root is x equals 3. Okay, if I have x squared plus 5x plus 4, another example, this is equal to, now two numbers that multiply together give me 4, add together and give me 5 are 4 and 1. If I set this equal to 0, the roots are x equals negative 4 and x equals negative 1. Two roots. Let me erase the other board, because we're going to prove a theorem that is kind of fundamental to being able to find rational roots. To find roots that are rational numbers. Now, if you have a polynomial like x squared minus 2, that has two roots, plus or minus the square root of 2. But those are not rational roots, by what we proved a little while ago. Square root of 2 is not a rational number, and so this theorem has no hope for irrational roots, but it does have hope for rational roots. And we're going to prove that. It's called the rational root theorem. So it's designed to answer the question, and it always answers the question, when is a root of the polynomial a rational number? And it's a pretty simple answer to check. So here's the setup. If p of x, I use this time, p of x is a polynomial of degree n, so it's going to be a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus blah, 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 all the way down to a sub 0. Where all of the a sub j's, all of the coefficients are integers. And n equals the degree of p, which means that a sub n is not 0. This term actually shows up. If that's the case, and, so a lot of ands in the hypothesis here, C over D is a root of P, where C over D, of course, is a rational number, so C and D are integers. Finally, a then. There's a then. The then is this. C is a factor of a sub 0, and D is a factor of a sub n. Okay, so if C over D makes this polynomial 0, then the numerator is a factor of the constant, and the denominator is a factor of the leading coefficient. That's what we want to prove. And believe it or not, it ain't too hard to prove. So proof. Since P evaluated at C over D is 0, let's plug it in and see what that means. A sub n times C over D to the n plus A sub n minus 1 times C over D to the n minus 1 plus plus A sub 0 equals 0. Now, let's clear the denominator. Multiply through by d to the n clears all the denominators, and now there are no fractions in here. So, multiplying by d to the n, what do we get? We get a sub n c to the n, because the denominator is now gone, plus a sub n minus 1, c to the n minus 1. Now, since I multiplied by d to the n, only n minus 1 of these cancel, but I've got a d surviving on top, plus blah, 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 plus, and of course a0 is multiplied by the entire d to the n, okay? And that's still equal to 0. Now here's what we're going to do. Let's isolate the first term and move all the other stuff to the other side. Okay, so a sub n c to the n equals minus a sub n minus 1 c, copy, copy, copy. But all of these now are minus signs, minus minus a0 d to the n, out of which I can factor a d because it appears everywhere. So I'm going to pull out that d and copy over the rest of this mess. Okay? Very good. Now, we may assume that C over D was in lowest terms. Typical trick. Assuming that C over D is in lowest terms. If it's not, then cancel all the terms that make them common and cause it to be in lowest terms. So C over D now is in lowest terms. And let's see. Since C over D is in lowest terms, D can't be a factor of C to the n. It can't be. Because if D were a factor of C to the n, then it would be a factor of, it would have terms and factors in common with C. And C over D is in lowest terms. So D cannot be a factor of C to the n, but D times something is C to the n times A to the n, so D must be a factor of the other one. If it's not a factor of this one, it's got to be a factor of that one. Therefore, D is a factor of A to the A sub n. Well, that's part of what we wanted to prove. So D is a factor of A sub n. Similarly, I'm going to save my similarly for the other board here. We're going to do the same thing on the other side to take care of C, and that'll be the end of the proof. So similarly, I'm going to come up to this equation, and I'm going to segregate the a sub 0 d to the n and shove all the rest of the stuff to the other side. So similarly, a sub 0 d to the n is equal to minus, and what do I get? Minus a sub n c to the n minus a sub n minus 1 c to the n minus 1 d minus, and the last one that survives, because a 0 d to the n is on the other side, so the last one that survives is a sub 1 c d to the n minus 1, out of which I can factor a c. So this is c times minus a sub n c to the n minus 1 minus a sub n minus 1 c to the n minus 2 times d minus blah 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 minus a sub 1, the c is gone, d to the n minus 1. All right. But again, since c over d was in lowest terms, d can't be a factor. C can't be a factor of d to the n. And so if it's not a factor of d to the n, it's got to be a factor of a0. Q, E, D. Because I proved before that d is a factor of a sub n, I've proved now that c is a factor of a sub 0, and bada bing, bada boom. Okay, so let's do an example. Find all rational roots. This is a beautiful theorem because you can have a pretty complicated looking polynomial and you really only need to worry about two terms of it. So find all rational roots of x cubed minus 4x squared minus 4x minus 5, setting that equal to 0. And in fact, I don't need to write setting it equal to 0 because that's a definition of roots. Well, how many candidates are there? I know that if there is a rational root, if c over d is a rational root, then c is a factor of -5, and d is a factor of 1. Well, what are the factors of -5? They're -5, +5, 1, and -1. And the denominator has to be a factor of 1, so that's either 1 or -1. So what are the possible rational numbers? -5, 5, 1, or -1, because all of those are divided by 1 and -1. So those are the only candidates for rational roots. Now, how do I figure out if one of them works? Plug the silly thing in and see if I get the truth. Always start with the easiest. Let's start with 1. If I plug in 1, I get 1 minus 4 minus 4 minus 5. 1 minus 4 is -3 minus 4. This one doesn't work. Let's try -1. If I plug in -1, I get -1 minus 4 plus 4 minus 5, which also doesn't work. If I try 5, then I get 125 minus 4 times 5 squared, which is 100, minus 4 times 5, which is 20, minus 5, which lo and behold is 0. So 5 is a root. And if I try -5, then I get -125. This doesn't look very promising already, because I'm not going to be able to cancel it with the rest of this stuff. Minus 100, it gets worse. Okay, so the only rational root is 5. Does that make sense to everybody? I wish I could hear your answers. All right. Let's try a little tougher problem. Okay. So another example. Prove the square root of 3 minus the square root of 2 is irrational. Well, here's how we're going to do that. Square this number. So square root of 3 minus the square root of 2 squared is equal to 3 minus 2 times the square root of 6 plus 2. All right, which is equal to 5 minus 2 times the square root of 6. Okay. Now, let's call this number x. So x is equal to that. So x squared is equal to this mess. So x squared equals 5 minus 2 root 6. So if I isolate the irrational part, x squared minus 5 equals -2 root 6. So if I square both sides of that, x squared minus 5 quantity squared is equal to this squared, which is 4 times 6. So I get x to the 4th minus 10x squared plus 25 minus 24 equals 0. So x to the fourth minus 10x squared plus 1 equals 0. And the only possible rational roots are plus or minus 1 divided by plus or minus 1. So the candidates are plus and minus 1, and neither satisfies the equation. So since neither satisfies the polynomial, therefore x is irrational, which is what we wanted to prove. Okay? So that's a good stopping point for us. Next time we're going to talk about upper bounds, lower bounds, and a very special couple of properties that are possessed by the real numbers. But for now, adios, and we'll talk later.